I can see from the conversation we've had before that people read that they should bring their questions from the website. So that's great, because that's what we love. My name is Joe Dietzel. I am one of the club members here, and I have been interested, and I got my first telescope when I was probably 11 years old or so, and it was a little spotting scope, and I didn't have anything like a mountain. I want to use some words, terms here, and you're going to see pictures later as to what I'm talking about. But I didn't have anything to put it on, so I remember looking at Venus like a pirate and seeing Venus for the first time when I was like 11, 12 years old, right? And I used to love to go out and look at Orion constellations. So who here has seen, knows what I say when I talk about, when I talk to say constellation? It's like a big group of stars, right? And they look kind of like pictures, right? And Orion is one that you can see later now, but it's starting to come up. And I remember it's really distinctive because you have 3 stars in a line that are expelled. Line. I always used to love to come out and see. So, title of the talk is So You Want to Be an Astronomer? And what I hope to talk to you into discuss with you guys today, have a conversation, is a little bit of the history of astronomy, a little bit of how you can do astronomy yourself. Everybody does. Part of the point of the history is to show, everybody started out with just their eyes. We're going to talk about some tools that you can use. And you can go outside and see there's binoculars, there's big telescopes, there's little telescopes, right? And each of them can show you different kinds of things. Right? I want to talk about, and what I really want to show is lots of pictures. This is a lot of pictures, and some of the a lot of the pictures I've taken myself in my backyard in Bel Air, right? All the light pollution in the festival and all of that. But everything you see is things that with the telescope you can now see, right? And I want to show the difference between what you would see in an eyepiece and what you would see with a camera, right? Because obviously I'm taking it like this. So this is a picture of a star, and it is the head of a constellation, Cygnus, the swan. Yes?
I was looking at the picture, and it kind of looks like the stars, like closer to the center.
Yes.
Forms a shape that looks like a tunnel that goes into the.
Kind of does.
Yeah, it kind of does. So you'll notice the star is blue. Blue color means it's a hotter and a younger star. Right? If it's blue color, then there's yellow stars like our sun, right? Kind of middle age, right? And then there's the red stars. Those are the ones that are old. That's because they're burning helium. Stars are made up of gases, right? Mainly hydrogen. And then it burns the hydrogen and it makes helium. And then it burns the helium and then it makes, I forget, but stars make elements, right? All the way up to iron, right? So all the elements that you see on the Earth, we are literally all made up of star stuff, right? Which is a really cool thing.
You've got a question already, Joe.
Yes.
Out of this area, it looks like kind of like glowing bouncy ball.
Yes.
A lot of stars do through it.
A lot of stars do that. Now you might notice that you see this big star, but then you see all these other little ones, right? Yes.
The reason why they appear a lot smaller than the big one is because they're a lot farther away.
Exactly. Cygnus, the constellation, You can see tonight. You look up almost directly overhead, probably right on you out, and you'll see something that looks kind of like a cross, right? And then there's a star at the head. That's this one. That constellation lies across the arm of one of the arms of the Milky Way. And all these stars that you see in this background are part of our Milky Way. Okay. I'm going to shoot us forward. So, watching the night sky is humanity's oldest hobby, right? Since people were walking around, they've been looking up and seeing what's up there, right? And you can see, come over here, examples of different kinds of things, right? So the indigenous peoples of the Americas, Indians, the Incas, the Aztecs, the Mayans in particular, they looked up and saw this great path of stars called the Milky Way. Unfortunately, where we are right now, it's very hard to see that because of all the light pollution. And we'll talk about that toward the end of my talk. But if all the lights were to go off, you were to look up, you would see this amazing streak across the sky that looks like that, right? Or this. And they believed that the Milky Way was where all their ancestors went when they died, right? The Mayan calendar, which was probably at the time the most accurate calendar, more accurate than the European calendars of that time, were based on very careful observation of the stars and planets, right? They referred to the Milky Way as Ane, right? And it was so big, and it caught everybody's attention. That was a key part of ancient people's lives, right? We mentioned Orion, right? You can see here a fairly nice picture of the Orion. You can see the belt that I talked about, and then he has the sword, right? This was a really important a constellation because it told the ancient people when winter was coming, right? Right? We know we're in winter, and they could also, when it passed by, when the spring was, right? Interesting fact, they figured out that the pyramids in Giza, in Egypt, right? The three big ones, they are aligned with the three stars in the belt. So what was going on in the sky was so important to people that they were building these huge megalithic structures, right, to model, right? Has everybody heard of Stonehenge? Right? That's basically kind of an ancient observatory, right? Over 4,000 years old. And it was used again to track the seasons. So why was it so important to track the seasons?
Know when winter was coming and then spring was coming. So, for example, you need to know how that for farming because at the time,
Exactly.
humanity and being so superior to undead people.
Exactly. Ancient people were dependent on farming and agriculture. They didn't have the Weather Channel, right? And they didn't have the local BAL weather radar, right? So they had to look at where the sun was rising and setting, where, everything that they could. And they were very, very smart, right? This last picture up here is one of my favorites as well. The story behind it as well. If you're looking in the sky and you see Orion, and you go that way, you will see a little cluster of stars. It kind of looks like a dipper, really, And for the younger folks here who have sharper eyes than some of us older ones, you'll look up there and I'll say, "Do you know what that is?" And they'll say, "It's the Little Dipper." Well, no. It's called the Pleiades, or the Seven Sisters, right? And it's that's for the seven major stars. And it's actually, if you look at it through a binocular, you get a chance, you're going to see it's a lot more stars than this, right? Huge, beautiful. In fact, my favorite way of looking at this particular thing is through a pair of binoculars instead of a telescope, right? Yep.
Isn't Greek mythology that's around it basically our seven sisters and the lion chases them down?
So that's the Greek version.
Yep.
The Indian version is that they were from the Kiowa tribe of Wyoming, was that they were 7 maidens that were chased by bears, right? And they ran, and they prayed to the Great Spirit, who raised up the ground they were standing on. So they went to the sky. And the place where that happened is where they said it happened. You actually explain not only the stars, but this very large formation out west called Devil's Tower, which is just like a big flat column up, right? And it has lots of grooves on it. They said that's what bears were scratching the on it. But there's a lot of different stories, kind of similar, right? Leo the lion, the bears, But it's kind of neat. It's kind of neat when you look at the history of how from very different places, very similar stories kind of come together. Okay. So we talked about the ancient people. Now we're going to talk a little bit about the evolution of modern astronomy, right? And this is one of the reasons that I love astronomy, because astronomy is one of the oldest sciences, and it is tied with the development of mathematics and scientific method. And these are a few of the people from the Western world where you can track that. Now, I would be remiss if I did not say that in the Muslim world of similar time, in India, there were also people who were watching and tracking the stars and making very accurate predictions as well, right? But from the Western perspective, things kind of get started. People have been looking at the sky and visually tracking what was going on. And who's heard of Copernicus? Okay. Copernicus said, from the Greeks, going forward, the general thought was, in Europe anyway, that this Earth was the center of the universe and everything rotated around the Earth. You see the sun do this, you see the moon do this. Doesn't it make sense? The Earth is the fixed point, everything else is moving relative to it. Yep.
Did that help inspire the phrase "the world does revolve around you"?
Probably. Probably. Which is yet another example of how astronomy has affected parents the world over. But Copernicus said, I've been watching these stars, and I've been watching these things called planets. And this doesn't make sense. I think maybe everything is going around the sun, not the Earth. And he based that on observations that he made and observations other people made. And the government power structure at the time didn't like that. So he was actually sentenced to death for saying the sun is the sun, the Earth goes around the sun. Right? Galileo, who's heard of Galileo? right? He read all the stuff Copernicus wrote. He said, you know, that's really interesting. I think it kind of makes sense. What am I going to do? Well, there's this new piece of technology that came in from the Near East, right? Called a telescope. They figured out if I got two lenses, I can get things look closer. So he was a very curious person, and he started making his own telescope, making his own lenses and things. And he started looking at some of these stars that were different. They're called wanderers, which in Greek means is planet, right?
Yes.
And they're ones that didn't come up the same time. Sometimes they were over here, sometimes they were over here. And folks were watching those wanderers and they're saying, "Oh, that doesn't look like they're going around us." Right? So Galileo said, "Hey, this telescope looks pretty neat. Why don't I point it at some of these wanderers?" In particular, he looked at the brightest one, which is Jupiter. And with the telescope, he could see not only Jupiter, but he could see 4 moons, 4 little bright dots. And he watched them day after day for many, many years. And he saw that those moons were actually going around Jupiter. Then he's gone, well, they're going around Jupiter. They're not going around the Earth, right? So he was one of the very first people to provide experimental evidence that challenged the way everybody thought about the universe. That's really pretty cool. There's another fellow that I really like. His name's Johannes Kepler. And he's the one that actually, by watching these planets and things, figured out the mathematics to describe the motion of a planet around the sun. He did that without a telescope. Just by watching how they moved and taking the time and their position over years and years. And he figured out that pattern, and he was able to come up with the 3 laws of planetary motion. What it? Who's heard of Isaac Newton? Okay, what did he do?
Cake.
No, not the fig.
Came up with the laws of physics.
Some of them,
Calculus. He invented
among
calculus.
other things.
Sure.
So Isaac Newton invented calculus. He invented the classical theory of gravity, which explains why planets go around the sun and why moons go around the sun. He invented the classical theory of optics, which explained why telescopes work. Did you see that great big telescope out there? That is based on a design from Isaac Newton. It is a Newtonian telescope that uses a mirror instead of lenses like what's in my glasses. Right? And he was a freaking genius. Right?
Fun fact, he was also born on Christmas, December 25th.
So,
Kind of a jerk.
who's heard of Einstein? All right? Einstein invented the modern theory of gravity, right? And general relativity, that's correct. So why do we need a modern theory of gravity if we had Newton, the freaking genius, figured out gravity? It's because people with their telescopes that have gotten bigger and bigger were tracking the paths of planets more and more, and they were looking at how, calculating how the planets should move relative to each other, and they were noticing it didn't quite add up. And because by this time we could make measurements much more precisely, we could measure smaller differences more precise. And Einstein said, well, it doesn't quite fit. So there's something we're missing. And he came up with general relativity. He came up with the modern theory of light, which is called special relativity. And that led to the very famous equation. Who knows what the very famous equation is? You over there? Yep. Absolutely. What does that mean? It means that if I take a particle and I speed it up to the speed of light, it turns into energy. Right? It shows that energy and mass are just different sides of the same coin. Yep. So he was a bigger genius. Right? But what I kind of want to show with this is how Copernicus, just looking up at the sky and tracking where stars are, led to the modern world. Quantum mechanics and quantum theory, which is why your cell phones work, right? Everything. All comes from a bunch of old guys staring up and watching the stars.
Hey, I resemble that remark.
Go to the next one. Now, this is a really important thing for you to gauge, right? Astronomy is not just for old guys with bad hair. And you might have got that impression from the previous slide, right? Okay, you can contribute to astronomy. Everyone, all your ages. Youngest person in 2010, youngest person to ever discover a supernova. Who knows what a supernova is? Okay, what's a supernova?
No.
Yeah, sure. Okay.
A supernova is a massive explosion that usually happens after a big star.
Well, it always happens after a big star collapses. Yes. So she discovered the supernova. This young lady who was 14 years old in 2008, she was the previous youngest person to ever discover a supernova. How do you discover a supernova? You go out every night, look up at the stars, and you notice what's going on. If you just go and look quickly, you just say, oh, that's what it looked like last night, right? But if you take time and look, you notice there are these little variations. And supernovas are one. And if you discover a supernova and it gets confirmed, you get to name it. Yes?
So, and also, it helps the general world, because I was, correct me if I'm wrong, the nervous sun, supposed to start what says, career, right?
Nope.
What is it?
Proxima Centauri.
Proxima Centauri.
Wide statement.
So, let's say the Alex was here, your 600, what's it?
Yeah, that'd be bad for us.
That would be really bad for us.
Yeah, they convert us. But also, the results of the exploding black hole could also most likely host people. Considering that supernova energy and matter to what cell
Okay.
stuck into it, even like
You go to the next one. So, how can we see these things? Right? How can you be an astronomer? Well, we already talked about it. First thing is just go out and look. And I'd like to do that all the time because I came with my optics already. They're not as heavy as some of my other telescopes. You can see, you go outside, you'll see, and there's just a lot to see, right? So your eyes, of course, are like the good first. You can see examples of this. I believe these are actually pictures of Mr. Musk's satellite trails, right? And has anybody looked at when the ISS, the International Space Station, has come by. You can see that. That's really cool, right? So another way you can do, and this is often a really good way to get started, is with binoculars, right? They give you a little bit of magnification, but they also give you a very wide, what we call field of view. That means how much I can look at. If I look through a straw, right, I'm going to only see just a little bit from the end of the straw, right? As opposed to if I look through a great big tube, right? That's what we mean by field of view. And binoculars can give you very good wide field of view and a little bit more magnification. And they're really good for looking at some of the larger objects in the sky that we'll talk about, constellations, right? And star clusters, right? Those are really neat doing binoculars. And you'll have an opportunity to actually look through some when you go outside. And of course, there's the telescope. That's my little baby telescope, right? It's maybe about that long. Got a nice little manual mount, right? And I like to throw this one in here. So there's one area now in modern times where you can use night vision technology. The same stuff that soldiers use, right? If you go and you point that up at the sky, all of a sudden, all that light pollution goes away. And you can see all these stars, right? And this is outside in the traffic circle outside my house, right? And you can see, again, I believe that's probably Deneb right there, that same picture that I took. And this is all that area has a lot of hydrogen that emits light, right? And you can see it light up. Okay. So telescopes. There's a lot of different kinds of telescopes. This is my big telescope. Right? This is a refractor. This is what Galileo used. It has what we call a lens here in the front. That is what we call an objective lens. And then it has a second set of group of lenses in the back. That's the eyepiece. That's what you look at, right? This is kind of what everybody thinks of when they think of telescope, right? There's a second type of telescope that we talked about. Newton came up with the main version of that. It is the Newtonian telescope. And that, instead of using a lens, uses a mirror. And this mirror is curved, right? And the light comes in like this. It hits the lens. It hits the mirror. And that kind of narrows down to a cone and a point. Just like here, the lens bends the light to come down to a point. And then it gets reflected up to your eyepiece. Right? So the advantage of this versus this is I can make these wider and gather more light. The more light I can gather, the more things I can see. Right? If I make a wider diameter lens for the refractor, I got to make it longer. Right? This diameter is like 6 inches. It's about that big around. This is 1.5 meters long. Right? It's about that high. Okay? That's a little hard to carry around. Right? I can get similar, a 6-inch reflecting telescope would be like that. Right? Then there's a third type that's a little bit more complicated. It does a couple of things. It's got kind of a specialized little mirror, or a specialized kind of lens on the front. The light comes in, it hits this mirror, it hits the second mirror, and gets shot out the back. Instead of here, it gets shot straight up. This is got a $25 name called catadioptric telescope. And it's making, you can see here, an example of what it looks like. And you'll notice I got my great big long one here. I got my reflector here. It's still long. It's not as long as that one, but it's still pretty big. And I'm sitting down. I'm a pretty big guy. And I'm looking through the eyepiece sitting down. That's still pretty big. This one has almost the same diameter as this one, but it's about that long. The reason it can do that is because it bounces the light several times, so it gets the same distance over a shorter overall, right? So these are kind of the three main kinds of, and there's lots of others, but these are the three main flavors of the telescope, right? Yes?
What would Hubble and James Webb be?
That's a very good question. They are basically Newtonian telescopes. They're big mirrors. And when I say big, I mean like the size of the wall back there.
I think they're also at 80 feet of purple
Yeah, well,
that I believe I forget like a
Mm-hmm. Mm-hmm.
and the image was 34
Okay.
perfect.
Okay.
yeah, they had to give the Hubble corrective lenses.
Yes.
Isn't it like this? But I was wondering, how are stars made?
That is a really good question. And there is no such thing off topic in this room. Okay. Stars are made when gas starts to coalesce and they get a little gravity, right? And they get the gas kind of comes together and forms little particles. And those particles start to come together and they form bigger, and eventually they kind of gets bigger and bigger and bigger, right? And the bigger the cluster of material gets, the bigger the gravity is, which pulls on and pulls on. And at some point, it gets so big that it starts squeezing the atoms so that they start to have a nuclear reaction. And that's when you get a star. Right? So we can ask some more questions later. Okay, so telescope mounts. So I showed you the telescopes. Mounts are important too. What do I mean by mount? Well, it's when I put the telescope on, right? So back in the day, you had stuff like this. So look at this guy, right? This is a schematic of an actual telescope somebody, and they got a crane holding the big. Look how long that is. And I'm not sure that was probably maybe 8 inches in diameter, something like that.
Sure was a very
Look how long that is. They had to use a crane to move it around. Well, that's a little bit difficult. But the general idea is what we call an alt-azimuth mount. And all that is it's like a cannon, right? I can move my telescope like this, and I can move my telescope like this, right? Like this and like this. That's really easy, right? Doesn't take a lot of stuff. It's easy to find the star, zoop, right? Got it lined up, then I can look through the eyepiece. Yep, there it is, right? The problem is the stars move. The planet rotates, right? So if you look at one of those, if I look at the Big Dipper when it's in the east, it's going to have an orientation. When I look at it later in the night in the west, it's going to be pointed in a different direction. And that's because the Earth is rotating, right? So if I am like with this setup, where I have a couple of my telescopes on one of these alt-azimuths, if I'm just looking at it with my eyepiece, I don't care. My brain can change one way or the other. But if I want to take pictures, I don't want to see stars rotate. If you guys can, this is a cool thing you can do in your phone. And there's an app I'm going to show you in a little bit, where you can just take your parents' phone or your phone if you have it, and you set it to expose. You set it out at the sky, and you get star trails, and you'll just watch how they go make a circle, right? So that's one area mount. And they could be motorized. This is an example of two motorized all-as mounts. These are manual, obviously. Well, a guy named Fraunhofer, probably in the early 1800s, right about the time that the photography became a thing, I really like to take pictures of these things I'm seeing in my eyepiece. But this isn't going to do it. So he came up with, and Fraunhofer obviously being German, what we call the German equatorial mount. And it looks like this, or that. Now, what do you notice? I got a mount that's at an angle, right? So I can set that angle so that this axis right here is parallel to the axis of the Earth. And if we get that right, then that's not going to move. And then all we got to do is move our camera this way and that way at the speed at which the planet rotates. And that means that I will keep my thing in frame the whole time. Right? And he developed it, and he had something that comes today. The way he developed this technique, this mount, before there were motors. So, but they were clocks. So he used basically the same kind of mechanism that you see in a grandfather clock to control the speed at which what we call the RA axis and have it move. Hence the term clock drive. That has stuck. So today, you will often hear in astronomy circles people talking about clock drives for their mounts. It's because back in the day, they were actually clocks, right? So it's really important when you're going to look for a telescope, right? Just consider the mount, because you want to have something that is, you don't want your telescope to be too big for your mount, right? Because nothing's more irritating than a wobbly, where am I going with that, right? So what can you see from your backyard? Well, obviously, this is a wonderful picture taken by another one of our club members, Derek George. He also took this beautiful one where the sun is reflecting off of it in red. And this is one that I took. What do you see that's different? Yes? Just shout it out.
It looks like the moon is a bit rusted on the bottom right.
Well, is that the only color you see?
There are also certain that I guess it is either shadow.
Oh no.
It wouldn't make sense because
It's green and there's purple. And there's a little bit of red.
our eyes filter out those colors, but because our pupils get better, we can't see those colors.
Yeah, you are 100% right. You are 100% right. But if you take a picture like this and you use some very careful manipulation and processing, you can bring out these colors that are very real. The green corresponds to a mineral called olivine, right? And that is what you usually find where volcanoes have come, basalt, right? The red, you would think that that's rust. You'd think that that's iron. But actually, they think it's volcanic glass that is of a specific diameter that kind of reflects the reddish, orangish light. There's some argument as to whether or not there might be some iron in there as well. And I forget what the purple is, to be honest with you. But it's pretty cool that the moon actually has color. What else can we see? Planets. I love planets. This is Mars. Look what we see on Mars. You see that? What that is? That's ice. right? Right? And you see reddish areas. Now that is iron, right? So when you see these other areas, you can see the decap. What's that? Who's this?
Down. Why you don't want it?
Yes. What's unique about Saturn?
Makes it dust.
Yes.
It's free.
Yep. You can see the color bands here. You can see the different rings, the striations. Okay. And this is the big guy. This is Jupiter. I love Jupiter. Right? You can see Jupiter. You can see 2 of the moons that Galileo saw. Right? You can see this. This is the biggest storm in the solar system. The red spot. Right?
Well, technically the rings aren't unique, but they're most visible with Saturn.
Saturn has the prettiest rings. You are absolutely right. Jupiter has rings too, but you never see them.
Yeah, because Jupiter's rings are all dust and rock. Saturn's are ice. So they reflect. It's like a lens.
Now, I might have mentioned I like Jupiter. When I'm watching Jupiter, you can see things besides just Jupiter. Everybody see this little dark spot? Right here? Right here? Right here? Right here? These are pictures that were taken at different times. And you see that spot is moving,
That way.
right? That's because right about here, there's a moon. And the sun is shining and the moon is casting its shadow over the planet. This is called a transit. And the moon that was doing that is Io. And this picture was probably the best. It was a little noisy that night, where you can just see the outline of the moon where the shadows cast. But anybody see anything else in these pictures? Yes.
So, the you already covered both Europa and Nile, right?
Nope.
Okay, then I.
Okay, so, well, Io is what we saw with the casting the shadow. What's this guy? What's happening here? Right?
You,
If you come up here, you can see there's a little pimple on Jupiter. Right? So the moons are going around, right? So Io is going in front. Europa is coming out from behind. Again, experimental proof that they're orbiting Jupiter. And you can see here, it's just coming out of the shadow of Jupiter. Here you can actually see it. You can actually see separation, and that it's farther and farther and farther. Right? So when you're observing, you can watch this stuff. Yes?
How frequently does something like that occur? Is that
Monthly. Right? There's a neat little I don't actually have that one on this, but there's this little app called the Gas Giants that you can download. That'll show you for any given time where the moons are and when these things are.
And if you look at the times too, you can actually see how quickly it happens. Like you can literally watch it happening because those moons orbit around it so
Yeah, it's
quickly.
about 20 minutes.
Great.
Thanks, Mom. Deep sky objects. We talked about faint fuzzies. This is what we mean by faint fuzzies. We can see galaxies. This is an edge-on galaxy. We can see nebula. You remember me showing you the big picture of Orion? Remember the sword? And there was like this red area? That's this. That's one of the few nebulas. If you're in a dark enough site, you can see by eye. Right? This is the Orion Nebula. And then you have these star clusters. This would be the Hercules star cluster. Right? And they're just, some of them, what they call open star clusters. They're just groups of stars that aren't really organized. Some of them are globular star clusters like this. Right? Yes?
the star clusters not being often.
There's quite a lot of them out
Yeah,
there.
there are.
Yep.
I can yak your ear off about globular clusters. So
Okay. So what would you see in the eyepiece? And what would you see with pictures? Because I show you a bunch of really cool pictures. And I'll be straight with you. There's a lot of processing. There's a lot of manipulation that gets those pictures to look that nice. Okay. So here's another cool. Yeah, I love Jupiter. Did I mention that? But here's another cool picture of Jupiter where I've got another planet, or another moon, and this I got a moon that's just starting to come, and I got the red spot, right? And that's been processed. This is what that picture looks like, most likely, through your eyepiece. Now, I can see a red spot. I can see this moon out here. If I'm very patient and I wait, I can see the little dot that's coming right here. That's a moon as well. But it doesn't look like that, right? Why doesn't it look like that? Because the atmosphere wobbles, right? And as it wobbles, the index of refraction changes, which moves your image in and out of focus. Now, if you are on a very, very still night, you can get things that look like that in your eyepiece. And that is an amazing experience, right? If you're on an average night, but you're very patient and you spend time looking, you will get periods of stillness where that will pop out, right? And your brain is really good. People don't realize this. Your brain will kind of do what we call the integration of the images that it's catching. So you'll pick that out. So, but this kind of gives you an idea. And this is one of the things that I always try to with new folks. I want them to understand, what they can expect to see in a telescope compared to what you see on the television or on your iPhone, iPad. Same thing's true for the deep space stuff. This is one of my, I like the Orion Nebula too. This has been very highly processed. Right? I've pulled out, you can see all the wisps. You can see the filigree. You can see the depth. It kind of looks like a three-dimensional sort of thing. Here's what it looks like in a telescope. Average. Now it depends. Now in the 20-inch telescope that's out there, it's probably going to be a little closer to this. It won't look exactly like that.
You
But
definitely
for-
see some color though.
But you will see some color for sure. Here, it's going to look like that. Because your telescope is mostly capturing green. Your eye sees, and it looks kind of black and white, right? Still pretty neat. You can see the center stars. You can actually see them probably better here. There's like 4 stars called the trapezium right here. If you stare long enough, you can see the kind of bat wings here, right? The 3 stars that we see right here. But it's not going to look like that. Here is M13, the Hercules. Again, this is a nice little cluster, all these different colors, fine little thing. Here's kind of what it's going to look like in a 4-inch, 3-inch telescope, small telescope. It'll look closer to that. And the globular clusters are one of the targets that actually come close if you get into a reasonable sized telescope, 8 to 10 inches. Right? They'll actually kind of come close to what you see here. All right? And then there's the Pleiades, right? And that's kind of where the strongest difference is, right? So they photograph here, look at all that blue, right? Those are what we call reflection nebula. Gas is coming, it's a little bit of gas around the stars, and it's reflecting the blue out of the stars, right? The eyepiece, maybe you can kind of see a little bit of difference in light and dark in there. Yes?
Let's see in all the pictures by like the eyepiece. It looks farther away than what the camera but
It's actually not, because I actually took these images and modified them so they look like what they are. So they're exactly the same size.
So it looks like that because our eyes are very, very bad at picking up colors.
Right?
Our eyes stink at picking up colors, but cameras are made for that.
So the reason they look different in terms of distance is because our eyes judge distance by how bright something is, right? And in the pictures, I pulled more light out, so I got more bright. So the technical term is what we call dynamic range, right? And that's just a fancy way of saying I have a bigger distance between what's really, really black and what's really, really white. And our brain says the distance between black and white is the difference between I'm up here and I'm over here, right? So that's why it looks the way you say it does. So you're not crazy. That's just the way your brain looks at stuff. Next one.
Yep.
So there's a new thing out there that is really pretty cool. And it's these robotic telescopes. And I don't think you'll see them in the United States.
Yeah.
But you come here enough, you're going to see stuff come out here. And they're basically a camera on a robot that can find, you push a button, it will find what you want to look at. You have your iPad, you say, I want to look at Orion Nebula. And then I push the button, and it will find it, and then it'll start taking pictures. Right? And when they first came out, they're really expensive. Thousands of dollars kind of expensive. But now, they're in the $300 to $500 range, which is still not inexpensive.
Oh.
But neither are the other telescopes. And I can tell you the amount of money that I have spent to get some of those nice pictures you got, 10 times more than that. Okay? For this little thing that I can buy, push a button, it'll go wherever we want. And you can see I had mine when we went to my parents' place to see the eclipse. You can see here's where the moon is going in front. Here where we are in totality. Right? And all I did was push a button. That's pretty amazing. Here are some examples. Just past Halloween. This is a nebula called the Witch's Bloom. And you kind of see why, right? Right? And this is, it's otherwise known as the Western Veil. Yep. And this is the Eastern Veil. And they kind of bracket like this, right? One's here, one's here. And in the center was a star that went kaboom, right? So these are remnants of the supernova. Right? And back.
I have a question. Is that an astronomer telescope?
So there's an app, and then there's the robo-telescope. And the robo-telescope controls the app. Mm-hmm. Yes.
That one kind of looks like a face.
It does actually.
Yes, it does. Actually, I can see it. I can see it. Yes.
Kinds of things. NASA has given detailed pictures.
Okay.
But look like that, were to get something like
So, okay.
Probably not that one.
Could I see the star? Yes. Are there people using this specific robo-telescope to look for exoplanets? Yes.
hello?
Yes. As well as the larger, more sophisticated ones. But yes, this little telescope, there are people who are putting a special filter in the front, and they're doing spectroscopy with that little telescope. So this is like a little science lab that enables you and I to do science we want. I mean, real stuff, right? Things that, to give you an example, we talked about supernovas, right? Who do you think was the very first person to capture on film, on video, the start of a supernova? You think it was the Jet Propulsion Laboratory?
Hint, hint. Not a professional.
You think it was James Webb?
James Webb.
No. It was an amateur in Chile with a telescope smaller than the big one out there and a camera like the one I used to capture a bunch of my stuff, who was in the right place in the right time. And he is the first person in all of humanity who has ever captured on film the start of a supernova. And all the astrophysicists were going, oh, give me your data, give me your data, give me your data. Right? 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 An amateur. That is what's so cool. I'm a professional scientist, but like that's my living, right? I do not astronomy. You can't do in your basement what I do, right? Is way more expensive than the $500 for that, right? But with relatively modest investment, particularly if you compare it to other hobbies like fishing and hunting and other stuff, you can do real science and see things that nobody else has ever seen. Right? Yes.
What are exoplanets?
Exoplanets. Okay. So for the longest time, the only planets anybody ever knew about were the ones in our solar system. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and I'm going to say Pluto because I think Pluto's a planet, personally. Right?
It's a very big problem.
Right? And for a long time, there were people who said, those are the only planets. There's no evidence there's any planets around stars. Right? And then in the 90s, people figured, well, if I watch very carefully how the brightness of a star changes over time, I can say, well, if that brightness dips by a certain amount, a planet has moved in front of it. And if I count that over time, I can count what the orbit of that planet is. Right? So that's what an exoplanet is, a planet that goes around a star that isn't our sun. Next one. Okay, so we're getting kind of the end here. I don't think I put anybody to sleep. That's always good. So I like to talk about some things. We talked about light pollution. And we started out by saying when the ancients, when they looked up, they said they were treated to this wonderful tapestry of the sky. If you go outside and you look up right now, well, you're going to see clouds. But if you were to go out, you see last night, you're going to look up and you're going to see, I could see maybe 20, 30 stars, right, with my eyes, right? If you go to a truly dark place, like Cherry Springs, which is a dark site up in northern New York, northern Pennsylvania, they don't have cell phone. That's how far out there where they are. You'll look up and you won't be able to tell what your constellations are because there's so many stars in the sky. I'm serious.
It's awesome.
It is amazing. You're literally going, where's the Big Dipper? There's no Big Dipper. It's because, you see the Big Dipper, you see boom, 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 right? Well, what you don't realize is inside the bucket of the Big Dipper, there's a bunch of stars, right?
Sure.
There's a little kind of high density area of stars. So it looks like the Dipper is actually holding something. The first time I saw that was when in Hawaii on a mountain, 9,000 feet up. And I'm going, oh my God, right? So light pollution is a real problem. And it's not just a problem because we can't see the sky, right? There are real negative effects. It impacts plant and nocturnal and animal physiology. It suppresses melatonin production and it helps with sleep disorder. It can cause a big change in migratory patterns, right? And of course, if you got your lights on all night, you have a huge energy consumption, a large carbon footprint, right? So there's ways that we can look at it. We don't have to get rid of the illumination. It's important to have when you're on a dark street and you want to be able to see where you're going. But you don't need lights like this. Well, what I want to see is down here, right? You have lights pointing down, directional, right? It's good, right? So that's something for you guys to think about, right? when you're picking your outdoor lights for your own backyard, you want to try to help things. This is an area that nobody really thinks about, nobody talks about, nobody takes for granted. But my own personal feeling is if we could see more of what was actually up in the night sky and we spent more time looking up, we'd all be happy. Right? We'll go to the next one.
Mhm.
So I mentioned there's a couple apps. Some that I like. This is a bunch. You go out to the thing to see. But I like Star Walk, right? And there's a free version, and there's a couple bucks, and you won't have to listen to ads. Star Walk is really nice. It's kind of I can put it on my phone and I can hold it up. And I think this is all going to be on our public Facebook site, so you can probably hit that as well. You can hold it up and you can say, what's that? And you hold it up and you point it and you can see it'll track where the stars are. It'll tell you where they are. Another app that I really like is Nightcap. A Nightcap is a basically a way of controlling your phone camera that allows you to have greater control over your exposure time and your illumination and your focus and that sort of thing. And it has specific modes for I want to take a picture of the moon. I want to do star trails. I want to, capture or meteors or whatever. Right? It's really, really nice. Who saw did anybody get to see the aurora a couple weeks ago? Was that not the most amazing thing in the world? I was blown away. I never thought I'd see. What do you mean?
Yeah, I mean, like, whichever one.
Right? Yes.
That's one thing you see that with the camera, but not with the naked eye.
Right, Lucian?
Is that what it is?
Yes, it is.
And cameras are way better at seeing things than our eyeballs are. Our eyes are terrible. Humans have really beat eyes. That's why we have to wear these things.
So I mentioned that thing called dynamic range. All right. The cameras particularly for the cell phones, because everybody wants to take night pictures, night selfies and whatever, right? They've really evolved the sensor technology so that you have this larger dynamic range. So you can pick up these fainter things and get better contrast, right? Now, we went out when I first ran out to see the aurora. We could actually see the color, but it looked kind of like a smeared thing. But then my son, who's got the newest and best phone, started taking pictures, and I'm going, "Oh my golly, yes, boy, come over here." Do that, but that's it. Basically, is the sensor's basically a little bit better tuned, particularly in color. Because your eye is most sensitive to green. So you might have noticed the green kind of stood out a little more than the red. But if your camera is sensitive across the whole thing, so it pulls all that. There are some, we have great, you guys have been out to our website and our Facebook, for books, if you want to understand what to look at. One of my favorite is one called Turn Left at Orion. And that basically is chapter by chapter in each season. What are the things you could see? What kind of telescope would let you see it? Right? And they have nice pictures, kind of like what I showed. That was my inspiration, putting it up there, of what you would expect to see in a telescope. Right? And then finally, the most important thing, if you're going to a star party, bring chocolate chip cookies.
Snatch are important.
Because that's a critical part of any star party, right? I do this for scouts as well, so just good thing to know in terms of hazards and safety things. What do we never, ever do? We never point a telescope or a binocular, or even just our eyes, at the sun, because you will hurt yourself. I cannot emphasize that enough. Never stare at the sun and never point a telescope at the sun.
Literally a laser.
Right? Unless you have very special filters. You're out there walking around. People got stuff everywhere. It's dark. Be aware of where you're walking, right? Try not to trip and hurt yourself or somebody's telescope. Or the scope. if you're observing by yourself, don't, try to observe in groups or partners or whatever. Stay aware of your surroundings. I'm not too worried about wild animals here, at least of the not too good type, in my backyard. Although I have been startled by a fox once or twice. But for example, the dark site that we were talking about up in Pennsylvania, they have bears, right?
Even the bears, they're little. They're black.
Yeah. They have bears, so don't leave your food out. Right? Bugs, right? Bug repellent, things like that. And then the weather, of course. If it gets cold outside, dress appropriately. Dress in layers. Right? Same kinds of things you do for other type of outdoor activities. Right? And now we're finishing up. I like this one. Right? Look at all the stars. What do you think it means? It means somebody stole it. Yeah. And I finish with these, right? So I've kind of run on a bit. I think the clouds were out, so I don't know that you're necessarily missing a whole lot outside, fortunately. But
see if it's cleared up a bit.
But what about a little bit over? Yeah. I'm happy to answer any questions that you might have. Yes, I figured.
Not that answer question.
Yes.
Would you be able to see any planet?